Hi, today I would like to talk about parent grain reconstruction in MTEC. So what I will cover today is an introduction to Martensitic transformations in general and to parent grain reconstruction from Martensitic microstructures, then the MTEC implementation of parent grain reconstruction mostly is going to be on the example of gamma to alpha prime transformation in steel. Then I'm going to show a few further application examples just to show a little bit of the versatility of this algorithm. And then at the end, I'm going to give a conclusion. So let me just briefly introduce you to Martensitic transformations if you don't know at all what they are. Martensitic transformation is technologically important diffusionist transformation from a metastable parent to a Martensitic child phase. Down here, we just see actually a transformation of gamma to alpha prime in steels. You can see that this happens more or less with the speed of sound and by diffusionless process very rapidly. So in steels, we know the gamma to epsilon transformation, that's austenite to hexagonal phase, and we have gamma to alpha prime transformation, that is austenite to a body-centered tetragonal phase. And both those transformations help with something called TRIP, which is transformation-induced plasticity, which is means of extending the ductility range of steels by transformation. So we also have transformation in titanium alloys. We can just have a look at this example where we form a phase called alpha double prime in beta. This is during deformation here. And yeah, we usually have the high temperature phase, which is beta, BCC, and we can transform this to a hexagonal phase, alpha prime. And we also have something called beta to alpha double prime, and alpha double prime is an orthorhombic phase, which is kind of like a not finished transformation to the hexagonal phase. So we also have two different Martensitic transformations in the titanium system, and this is also used for TRIP, but also for the shape memory effect. So in Martensitic transformations, the orientation relationship is usually defined by a parallel set of planes and directions of the parent and the child phase. So in steels, in the case of gamma FCC and alpha prime BCT, we have the most famous Kodymov-Sachs orientation relationship, where we have the 1-1-1 plane of austenite parallel to the 1-1-0 plane in martensite, and the 1-1-0 direction in austenite parallel to the 1-1 direction in martensite. Then we have Nishiyama-Wassermann. There's a different one, and there's tons of other, let's say, orientation relationships within steel that are quite close to each other. I'm not going to go into all of them. Here we have the Shoji-Nishiyama orientation relationship, and this one is actually for steel, austenite to hexagonal phase. So here we have the basal plane parallel to 1-1-1 of austenite, and then we have the 1-1-2-0 parallel to 1-1-0 in austenite. So with all these transformations, we actually have something called orientation variants, because the crystal symmetry in a crystal leads to the formation of several of these orientation variants. Let me just show how this works. So when we have one certain 1-1-1 plane here in austenite, we actually have 6 different variants of martensite that we can form from this, because we have a lot of different 1-1-1 directions in martensite that can be parallel to different 1-1-0 directions of austenite for this plane. So we have those 6 variants, and since we have 4 different 1-1-1 planes in austenite, we actually end up having 24 variants for the case of FCC to BCT transformation. And if we plot this in a pole figure, we actually get these variants right here. That's how they look for the Kodymov-Sachs orientation relationship. So the symmetry actually gives us more than only one variant that can form. To make this even a little bit more complicated, the experimentally observed orientation relationship is generally close, but absolutely not identical to the rational orientation relationships, with the rational orientation relationships meaning the ones we just saw with parallel planes and directions. So in Lath, martensite, and steels, actually the orientation relationship is somewhere halfway between Kodymov-Sachs and Nishiyama-Wassermann. We can see this down here. So this is the ideal rational orientation relationship where we have the parallel planes here between martensite in blue, and austenite in red. And if you look at the experimentally observed orientation relationship on this pole figure, we can see that the parallel planes down here, they're quite close. So the experimentally 011 martensite planes are quite close to the 111 in austenite. But especially if you look at the parallel directions, we can see that we have Kodim of Sachs right here, and Nishiyama-Wasserman around here, and that we have the experimental 1 -1 -1 martensite orientation somewhere in between those two, actually very close to something called the Kelly orientation relationship, which is not really a rational one. So between Nishiyama-Wasserman and Kodim of Sachs, we have a couple of degrees. I think it's 5.5, and then experimentally we are somewhere in between those two. And this actually becomes quite important later on for the parent grain reconstruction, as I will show later. So let me now, after having given an introduction to martensite formation, talk a little bit about parent grain reconstruction. So parent reconstruction aims at calculating the parent microstructure from the orientations of the child phase. So we can see here that we have a microstructure of child grains. So this is Lath martensite, alpha prime. And this, of course, has formed at some point by cooling down the microstructure from high temperature when it still was austenitic. And then during cooling, we get this martensitic transformation, which makes us end up with this kind of microstructure. Then when we do an EBSD scan of this microstructure, we might want to actually figure out what has the parent orientation looked like. And by parent grain reconstruction, we can figure out by the relationships of these child grains with each other what the parent phase has been before the transformation occurred. So we actually go, we inverse kind of this orientation relationship to go back and reconstruct the parent phase, which I have an example of right here. So what's interesting now, or what makes this task non-trivial, is that one parent orientation can, of course, form several child orientations. We can see this here, that, for example, the yellow grain has formed a lot of different orientations, and these can be up to 24 in steel. And this actually also means vice versa, that one child orientation can have multiple potential parent orientations. And this is because of in this case, the symmetry of the child crystal, that we, for one, let's say, martensite grain, we can, but in theory, have different parent grains that could have formed this martensite grain. So just by looking at one grain, we cannot say what the parent orientation is. So what we need is actually, we need to find sufficient distinct child orientations of the same prior austenite grain that we can calculate the parent orientation. So if we have a couple of these, we can actually narrow down the orientation of the potential parent grain to a couple of orientations, or all the way down to one orientation. And in steel, this is still a very difficult task because we have so many variants in both directions because of the high symmetry of a cubic to cubic transformation. In other systems, like in titanium, we're actually a little bit more limited in the amount of variants we can form, and we can see that the reconstruction is a bit more straightforward. So we have this martensitic microstructure here, and yeah, let me take the slides in the right way. So why should we care about parent grain reconstruction, right? It could seem like this is only an academic exercise that we do because we want to, calculate variance back and forward, and it's a nice way of passing away your time. But no, it's not that case. Like that. The parent grain reconstruction is more than academic exercise, and there's two reasons for that. We want to optimize the high temperature processing conditions. So we have maybe hot rolled or forged this material here at high temperature. Then we get the martensitic microstructure at room temperature, but we want to analyze how do the rolling parameters or forging parameters have actually shaped this austenitic microstructure before it transformed to martensite. So we need to reconstruct this in order to get to the parent phase microstructure, which then helps us to see how the thermomechanical treatment has influenced this kind of structure. And furthermore, if we want to do a detailed analysis of the hierarchy of martensitic microstructures, then we also actually need to do the parent phase reconstruction, because we can look at these grains here, we can say something about the orientation, but we cannot really say which variants have formed and which packets they have formed, how this austenite grain has been partitioned into the hierarchy of martensite. But we can do this if we know the child orientation, we know the parent orientation, and we know the orientation relationship. Then we can actually assign variant IDs, so of the orientations here, or packet IDs to these Martensitic grains, which means that we can do variant analysis. So we can actually plot the packet map here, and then go into one grain and actually plot all the variants that have formed. So this is only possible if we do parent grain reconstruction, which is why it's an overarching important technique to develop further in material science. So to give you an introduction to what has happened in the field so far, I think the first algorithm that really also managed to reconstruct some martensitic microstructures was presented by Chiron in 2006. I have to say martensitic child structures. Before that, I think Humbert have been doing some work on titanium variants, which I said is a little bit easier. And all the methods that have been proposed by now, here's an overview of the references to them, can basically be split into two different categories. So there's one category which could be called operations on a weighted graph constructed from a grain map. This is something we see here on the right side. So we have all these grains in our microstructure, and we then look, okay, which neighbors do the grains have, and so these are all martensitic grains. And then we can see, okay, how well do the neighbors actually fit to an orientation relationship? And this red boundary here, for example, would then be a boundary of where we can see the orientation relationship between the neighbors doesn't apply very well. So we can kind of gather all the grains that belong together and then do the reconstruction on these. And then there's a second method, which is operations on crop sections of the orientation EBSD map that has been segmented into a square grid. So that we can see down here. The dots are actually individual measurement points in our EBSD data set, and then we take a crop region, and for this crop region, we do a reconstruction of that region based on the EBSD points we have in here. This is a lot more computationally inefficient because we need to go through the entire data set instead of just taking the graphs, but it's claimed to be more accurate on ambiguous orientations such as twins. I have no personal experience with the second method, but it's something I might look into at some point. So most of the weighted graph approaches, which were the ones between the grains, they first calculate all the possible parent orientations for all the child orientations, and then they group the child grains that have a common parent orientation. So this is possible, but it's also quite computationally inefficient because we have to calculate all possibilities before we can even start grouping grains together. And there is a method that has first been proposed by Gomez and also by Nysenen, which applies Markov clustering as a clustering algorithm. And here we first group all the child grains based on their fit to an orientation relationship and then calculate the common parent orientations. And this Markov clustering discovers natural groups in graphs by simulating a random walk. And we later on going to see this a little bit in action to understand better what it's actually doing. This is one of the algorithms that has been implemented in MTEC now. So let's have a look at the MTEC implementation. It's, as far as I know, the only open and freely available parent reconstruction method, and it's released with MTEX 5.6, so recently has been released. It supports the analysis of transitions between arbitrary parent and child phases, so you can take any crystal system you like, as long as it somehow makes sense in the orientation relationship that you enter, you can analyze it with MTEC. And there's different reconstruction models that can be combined. So the whole code has been written very modular in a way that we can combine different methods together depending on the task at hand. So there's boundary-based versus triple point-based algorithms. So most of them are boundary-based, but we can also look at triple points and where we have three, let's say, orientation variables coming together to form what we could call a nucleus. So a point where we kind of know the parent orientation. Then we have graph clustering algorithms. That's the one I just briefly scratched on before, the Markov clustering. Then nucleation-based algorithms, we can have child grain reversion by vote of neighboring child grains. So that is actually what is in the triple point base, that we can revert our childs based on the neighbors that we have around. And we can have growth-based algorithms that we grow a parent grain into the child grains. So once we've maybe have some areas where we, with good confidence, know the parent orientation, we can then by voting mechanism let those parent grains grow into the child grains. I think a very powerful tool is the straightforward local reversion of bad reconstructions. So you can, by setting some criteria, you can revert microstructures and the reconstruction of that locally where it was not so good, and then you can maybe take a different approach to finish the reconstruction. And also this we're going to see in action later on. And then in the end, an iterative reconstruction with increasing threshold. Yeah, that's basically what I just said. So we can actually iterate over maybe different reconstruction methods and then slowly increasing the threshold to allow, let's say, worse results. And so we start with something very good, then we let it grow a little bit, and then we use something different maybe to finish off the reconstruction. I'm going to show this later. And yeah, this is a short commercial break. There's also an add-on to MTEX called ORTools, which is something I've been developing together with my colleague Dr. Asya Gaster from the University of Wollongong. Yeah, it's an add-on to the MTEX focusing on phase transitions. It has a function library for orientation relationship discovery, analysis, and the plotting of publication-ready figures of Martensitic transformations in MTEX. So this is basically a little bit more of a turnkey solution for doing all this analysis with already pre-written functions, pre-written plotting functionalities. So the library contains several automated and pre-formatted plotting functions, interactive exploration of several orientation relationships in one EBSD map, which I find very exciting. We do transformation texture prediction. We have a lot of useful auxiliary functions that make the use of MTEX easier, and there are more things to follow soon. So you can visit the repository right here, and there's actually a nice video series where I've guided you through 5 different examples on how to use this ORTools library to explore your martensitic microstructures in EBSD. So again, all the difficult nitty-gritty technical stuff is in MTEX about phase transitions, and this is basically something we put on top of it for specific to analysis of martensitic transformations that makes your life easier in plotting things and gives a couple of extra functionalities. So if you're interested, go and check it out. Yeah, and actually we're gonna start with this example 1 now, which you see right there. So example 1 is also the example that is on the MTEX homepage in the documentation of martensite parent grain reconstruction. And yeah, we have the parallel example 1 in this ORTools toolbox where we show a little bit on how these functions are being used on the same example. But they both do the same reconstruction because all the technical stuff is in MTEX. So we have this microstructure here on the left side, which is a martensitic microstructure, obviously in steel. And we want to transfer this EBSD Lath martensite microstructure on the left to an austenite microstructure on the right side. So this will be our end result. And I'm going to guide you now through how this can be done. So let's first have a look at the initial microstructure. We can see that we have only martensite. This is a phase map. So everything is alpha prime. Nothing interesting happening here. Then we can have a look at the initial orientations in the microstructure, and we can see that the prior austenite grain boundaries are not obvious everywhere. I mean, you can, for example, see that this is probably formed from one prior austenite grain. The same could be true for this part here, but then we have some regions like down here where it's not completely obvious, or here. So it will be good to have some kind of automated procedure that actually looks at the orientations and can figure out what the prior austenite orientation has been. And actually, it's not that obvious in this map, but we have 29% of unindexed points. So that's quite a lot. We can actually see a scratch going through the microstructure here and here. Of course, this is not ideal for a data set, but I think it serves as a good point to show that we can still reconstruct a data set even though we don't have like a perfectly clean data set. Yeah, we will see that that is actually possible. So what we have to start with is the orientation relationship determination. As you remember before, we can assume Kodim of Sachs or Nishiyama-Wasserman, but we saw that actually the actual orientation relationship lies somewhere in between those two. And we can actually show this with MTEX. So we start with a command called parent grain reconstructor. So this is the new class that has been implemented to kind of manage all the reconstructions. So you put in your EBSD data set, you put in your grains that you've reconstructed before, and then you make an object called job. And in job, you have all the stuff you want to know about the reconstruction. So then the next line we can say we want to actually we want to define the orientation relationship. So P to C stands for parent to child, and this is kind of the misorientation that defines the orientation relationship between the parent and the child phase. And we say in the beginning, let this be Kodim of Sachs. So what we do is then we do job.calcParent to child, and this is a routine that iteratively checks how well the microstructure misorientations locally fit to this P2C, to this misorientation, and it will find the grains that fit very well to it and look at the actual misorientation of these grains and then make a new approximation for this P2C based on the actually observed misorientation. And then we basically iterate around and do this again and again and again. And we can see down here that the misfit of the actual orientations between the grains with the orientation relationship decrease slowly with a better orientation relationship. So this iteratively compares our orientation relationship in job P2C with the actual misorientation of microstructure, and then iteratively refines our orientation relationship based what we have experimentally. So you could call it an experimental refinement. And this has been first presented by Nusan et al., who's going to be the next speaker, by the way. So we can actually have a look at the disorientation of our local boundary misorientations with the orientation relationship. And we can see for Codium of Sachs, which is represented in this pull figure, these are all the Martensitic variants. We can see that on average, maybe we have 4 or 5 degree, I would say maybe 4 degree of misfit between the actually observed or misorientations at the boundaries and this Codium of Sachs orientation relationship. We can do the same for Nishiyama-Wasserman. We can see that this is even spread out even further, maybe even a little bit better fit, I would say. But still, we're quite far off from the orientation relationship. We're quite far off from what we experimentally have in our microstructure as an orientation relationship. We can also see by assuming Nishiyama-Wasserman orientation relationship that all the 24 variants we have here, they actually collapse to 12 variants by this. So we actually reduce the amount of variants between those two because we kind of overlay an identical symmetry. So now let's have a look at this fitted orientation relationship. So we use this calc-parent to child to find the experimental orientation relationship. And if we then look at how large is the misfit between the actual boundaries and this experimental orientation relationship, we find that we have a peak at around maybe 2.5 or something. So we can still not completely make this to 0 because there is a spread in the data set of orientations, but this is basically the best we can do. We can see we're far better than with the Codium of Sachs or Nishiyama-Wasserman orientation relationship. And we can in fact see, if we look at these variants right here, that the Codium of Sachs variants have moved closer together, but not as close as they would in the case of Nishiyama-Wasserman. So we're kind of somewhere in between those two orientation relationships, it seems, which kind of confirms what we saw earlier. So one thing to note, if we do cubic to cubic orientation relationship, MTEX automatically assumes a Morito convention. So the convention of how those variants are sorted and numbered, is actually saved in job.variantMap, and this is here the default order, and this gives us the Morito convention in Martensitic steels, which basically tells us that on one packet, so the packet, the 111 plane be here, and these are all variants that would have formed from one packet, that these are numbered accordingly. So you have 1, 2, 3, 4, 5, 6 for the first packet, and then we continue for the second and the third and the fourth packet. It's just the convention that's usually used in steels quite a lot to know when we talk about variant 10, which one do we actually mean, and we can compare this between literature. And this is assumed per default now if MTEX detects cubic to cubic martensitic transformation. So now we can actually inspect your orientation relationship after we've done this, and we can actually use this command job.parent to child info to spit out a lot of info about this orientation relationship. So we get the misorientation angle between the parent and the child phase, which is close to 45 degrees, parallel planes, parallel directions, the misorientation rotation axis, and then we get all the different variants here. I only showed 2 right now with their misorientation to each other. So let's look a little bit more in detail what this actually tells us. So before we said that often experimentally or generally experimentally you have your directions somewhere between Codium of Sachs and Nishiyama-Wasserman. And this orientation relationship that has been posted here is actually the closest rational one is actually Nishiyama-Wassermann now, even though we start with Kodymov-Sachs. So we have the 100 here, the 1 minus 10 right here, and then we have 111 parallel to 110. So this fits Nishiyama-Wassermann, but something you might notice is actually that what we have as closest planes here is the closed directions, and the closest directions are the closest planes classically. And that's just a little bit of a shortcoming right now, that MTEC cannot really distinguish which of these two faces is the BCC and the FCC face, and it doesn't really know what is the interface between those two. It can only say that, okay, I found that 111 is parallel to 110, and of course directions and planes are the same in cubic faces, so MTEX can just not distinguish these two cases. So these can just as well be reverted. But what we see now is actually that this, what we usually know as a direction here, and is written as a plane here, is 2.4 degrees off from experimentally from this closest rational. And this is actually very close to having Nishiyama-Wassermann here as the closest rational orientation relationship, and then having 2.4 degrees, that's roughly what we see right here. So this actually confirms what literature shows us as well. And then another thing, if you look at the OR misorientation axis, so they're all like minus 0, something, 0, something to 0.3, and here also 0.3. So this is basically a 0, 1 axis, both of course in the parent austenite and in the child face. So the misorientation axis between the two faces is 0, 1, and that's actually the Z axis right here. And then we have the misorientation angle. This is very, very close to 45 degrees. So this actually shows us the general kind of misorientation between the two faces here. So you can read all these things and get all these things from parent to child info. This will, of course, help you also if you need something maybe for a TM examination or something. You need to know which variants do I have, how are they related to each other, which reflection or zone axis do I have to look for. Then one more feature, like the variants, they're basically also all plotted here, and they're all basically shown as misorientation, axis, and angle to the first variant. So these are basically misorientations to what we call a variant 1. So this kind of shows us what kind of misorientations we expect on the martensite to martensite grain boundaries. And if you look closely, we can actually see that between 21 and 49 degrees, there's nothing here. So stuff is either below 21 or above 49. And now let's maybe have a look at the plot of the boundary misorientation for all the martensitic grains. We can see here, this is kind of the angular misorientation at the boundary. And there's this region here basically that is not represented in the orientation relationship. And if you look at this, is from kind of light blue to orange. And we can see everything that's light blue and orange actually already looks like a prior austenite grain boundary, which is not an OR boundary. So actually looking at this, we can already figure out some of these boundaries definitely cannot be martensitic boundaries, but that they have to be prior austenite grain boundaries, which are not related by an orientation relationship. So we can see those boundaries going here, and we can kind of grasp already where the austenite orientations would be. So now let's have a look at the disorientation. So the disorientation is the same plot as we had before, just now this time we want to plot this onto the grain boundaries. So we show on the boundary how large the misfit to the orientation relationship on that boundary is, or disorientation for that matter. We can now clearly see if we threshold the disorientation to 5 degrees, so everything that's above 5 degrees also shown in red, that we can definitely probe the prior austenite grain boundaries very easily by comparing all the boundary misorientations to the orientation relationship. And it seems that we're getting somewhere with this experimental orientation relationship here. But of course, we can also see that in some boundaries, for example here or there, we locally kind of lose this dark red contrast, which means that just by incidence, we sometimes might get misorientation between prior austenite grains that do resemble also martensitic orientation relationship boundary. And this, of course, can sometimes give us problems when we try to reconstruct the microstructure. So this is something you can see in this kind of plot. So the same thing can also be expressed as a probability. So the probability is something that is calculated in calc-graph. And calc-graph is now the first part of this reconstruction with a clustering algorithm. So first we look at all the child grains, so all the martensitic grains, and we connect them to their neighboring grains in a graph, which looks something like this. So all the nodes would be the grains, and the connectors are basically neighborhood relationships. And then we can assign to each of these links a probability that this link represents an orientation relationship link. So in this case, we can translate this disorientation into a probability ranging from 0 to 1, whether a boundary is likely to be orientation relationship related or not. And we can see here, of course, that the prior austenite grain boundaries are shown to have a low probability to belong to an orientation relationship. So this is internally done when we do job.calc-graph. We calculate the graph between the grains, and we look at, okay, how likely are the boundaries between those grains part of an orientation relationship. So the next part is cluster graph, and clustering is now actually what we do with the Markov clustering in this in this example. It's currently the only clustering algorithm that has been implemented, but one could of course imagine using different clustering algorithms in this object as well. So what it does is basically now it basically inflates and contracts, inflates and contracts the metrics of all these points. And what this does, it simulates a random walk. So the idea is that you're less likely to walk from one grain to another grain if the likelihood of these being a part of an orientation relationship is low, and more likely to walk from one grain to another grain if the orientation relationship probability is high. In this way, what the clustering algorithm does, it's like slowly gonna break the links to grains that are likely not belonging to an austenite grain, and it forces the links that that are very likely related by an orientation relationship. And this way, through many iterations, we then get into groups with like nodes that are likely belonging to one austenite grain. And we can actually plot these clusters that we get out of this Markovian algorithm, and we can see that most of the clusters lie within what we can identify as an austenite grain. There seem to be more clusters than there are austenite grains, so it's still a bit segmented into smaller clusters, but we can also see that we have several variants in most of these clusters that they're probably going to do a good job in reconstructing. We can also, with some parameters, steer how many clusters we want, if we want more fine-grained clusters or larger clusters. And both, of course, have their disadvantages. So this is what everything looks after the clustering algorithm, and we kind of identify child grains that probably belong to the same austenite orientation. And then in the next step, we then calculate the parent orientation from those clusters. So if we have, for example, 10 different austenite 10 different martensite grains, we can then calculate the parent orientation for these martensite grains and figure out, okay, which is the matching parent orientation that all grains agree on. And then we can actually flip this this cluster around to an austenite orientation. And when we do this, we get this microstructure, and you can, I guess, definitely see that we get a reconstruction that looks quite nice. So we can definitely see the austenite grains here, and some of them that we suspected earlier to be one grain actually also form one grain. But you might also be able to see that some of the smaller clusters here, they don't seem 100% right, and maybe there's still some errors in this kind of reconstruction. And that's something we're going to look at next. So, because what we can do is when we reconstruct the grains, we can actually calculate a fit between how well does a local, let's say, martensite grain transformed with the orientation relationship to the austenite grain fit with the overall orientation of the cluster. And if that agreement is not very good, we actually get a bad fit, or let's say a misfit of, in this case, higher than 5 degrees. And those grains are likely to be wrongly reconstructed, right? Because they don't really fit with the rest of the cluster, then they're maybe in the wrong cluster. The same thing we can do for very small clusters. We say, okay, if there's that small, maybe we didn't have enough data points to actually do a confident reconstruction. So we can plot, of course, what we think is not a good reconstruction, but we can then also use this job revert. And I think it's a very, very powerful command to revert the reconstructions that we don't like, and we kick them out. And then we get this kind of this reconstruction where we have gaps in between, which have been created by all the reconstruction that has been thrown out because we were not confident enough of it. And you can, of course, for your own data set, look, does this make sense? Does it not make sense? And adapt these values to what you're confident with in your reconstruction. Because in the end, in your reconstruction, nothing is 100%, and it depends on how good you want to be and how confident you are of what you're doing. So now we still have a lot of empty regions, and we of course would like to somehow also take care of these. So now doing a clustering algorithm is a little bit bad because we only have those small regions and we can only make small clusters, and it already didn't seem to work that well in the first case for these regions. So we have a different algorithm we can use now, and we can use this calc parent from vote function for that. So what are we doing when we do this? We actually want to grow these austenite grains into the gaps now. And how do we do this? We use this job calc GB votes, and this one calculates all parent orientations from a child orientation by applying the orientation relationship and then finding the best fitting parent orientation with the neighboring parent grains. So let's have a look in detail what this means. We have this area which has not been reconstructed, and we can now say, okay, this martensite grain here, let's apply the orientation relationship and calculate all the parent grains. And then we can see, okay, how well are the 24 potential parent orientations, how well do they fit with the neighbors? And we will figure out that the best fit with the pink kind of grains has been 1.8 degrees, and the best fit with the purple region has been 5.7 degrees. And on this base, we could say, okay, it seems quite likely that this grain maybe fits to the pink region. And then with calc parent from vote, we can then say, okay, if this fit has been better than a certain threshold, then please revert it. So we can also say, okay, if the best fit is 10 degrees and the second best is 25, then we're not happy with either of them, and please don't reconstruct anything. So you can kind of steer this process. So in this case, we got a lot of pink grains here because we said if fit is better than 7.5, do the reconstruction. And of course, by iterating this thing, the parent phase will gradually grow into the child phase. So we can, because in the next iteration, of course, we have again more parent phase, and the parent phase can grow piece by piece. This can also be applied in cases when a lot of parent phase is retained. So if we have a lot of retained austenite, for example, in the beginning, we don't even have to start with clustering, but we can immediately go to this and just let the retained austenite grow into the parent phase. We have an example of that later as well. So after having done this, we then actually can fill up these regions, and we can see that a lot of the regions that have been a little bit ambiguous before now have been solved a lot better. But still, we also have some regions that are not reconstructed, especially at the boundary regions, because here we don't really have a lot of neighboring grains because we're at the boundary. And yeah, we could, of course, now raise the threshold and just force to have more reconstruction, but one has to, of course, decide what's reasonable and what's not, and we decided to stop right here. So then we can use commands like job merge similar and job merge inclusions to merge grains that have a similar orientation, and also to swallow up small inclusions. And then we go from this kind of map to this kind of map. And these are then our reconstructed grains. So just a fast comment on the computational performance, because often people think that MATLAB is quite slow, and that's true, but not generally true. Of course, Fortran C++ can be a lot faster, but if you properly vectorize your code, MATLAB can be quite fast. And I think in this case, Ralph has made sure that this is the case, which means that this example here is a 400 or 500 times 700 point map of 21,000 grains. And this reconstruction in 2 stages that we just saw took 1 minute and 16 seconds on a conventional office laptop. And it concludes all these steps. And if we run the entire script, which goes from reconstructing the grains in the beginning all the way to variant analysis and plotting 13 publication-ready figures, as in the example of ORTools, this is actually 3.5 minutes. So I think all in all, this is a quite fast toolbox. So then we can also reconstruct the EBSD data. It can all be done with this small command, and then we can calculate the EBSD data based on the parent orientation from the grains and the EBSD data of the child. So generally, I think the agreement, if we now look at the Martensitic grains and the parent grains, is quite good. But we also see that some of the grains still look quite unnatural. Could, for example, look at this grain down here, which is from this area. We can see that we have a dark blue area and a dark blue area separated by a white area. And in red, you can actually see I marked what is a twin orientation relationship. So here we actually have a twin orientation relationship between those two. And yeah, the next speaker, Tuomo Nyson, will actually talk about this issue that we have in parent grain reconstructions when we have annealing twins in austenite. And this is likely the case right here. Because if you look now actually at what the martensite orientations have been, it's very unlikely that actually this boundary here goes through an area where we have almost the exact same variance all the way around. And it's maybe more likely that the boundary should go here, or maybe that all of them are part of one grain. So yeah, this is something the next speaker will go a little bit into. So let's now have a fast look at variant analysis, and here we want to showcase some ready-made functions from ORTools as well. So we can use command calc variance, and then we can plot a map of the variance. And this is then the map, and we have the prior austenite grain boundaries on top of that, and we can see the variance colored from 1 to 24. And then we can actually also go to different grains and, of course, look at the variance in a pole figure. And we can get area normalized frequency map for a certain grain to see which variant has been most dominant in a certain grain. We can do the same thing with the packet IDs. So here we have the 4 packets, and we can get the pole figure for that and a histogram with that. And yeah, in ORTools, we have this function called grain click, which is quite cool because you can click on certain grains and then get all these maps for this certain grain. So here we have a parent orientation, the child orientations, then the packets and the variants for this grain. And we can also do plots of, this is here, for example, the average austenite orientation with the experimental spread of the orientations, then the theoretical variance on top of that compared with the experimental variance. So you can do a lot of cool things with once we've reconstructed the parent austenite grains. And yeah, we have automatized a lot of these things in the ORTools toolbox. So now I will briefly go through a couple more examples, but I'm just going to show the application and not go through the details because otherwise we run too much out of time. So this is a titanium 10 vanadium 2 aluminium 3 iron microstructure. And after cooling down, intercritic annealing and cooling down, we actually get something like this. It's beta is the high temperature phase. Then we have alpha, which is a phase that forms during a heat treatment, and then during cooling, if beta is not stable enough, we have a martensitic transformation to alpha double prime, which is an orthorhombic martensitic phase. So everything here in yellow is martensitic, everything blue is neither a parent phase nor a child phase of the martensitic transformation, but just a tertiary phase. And in green, we have the parent phase we kind of want to reconstruct to. So here, we now have the reconstructed microstructure, and based from that, we can then color the individual variants in the microstructure and do variant analysis in each of these grains. And since we have a lot of, let's say, a retained parent, we can actually go through this kind of this kind of loop with letting the parent grain grow or doing the clustering. Both actually works quite well. And this alpha phase here is actually just ignored in this case. So then the second example on the MTEX homepage, and this is also the second example in the ORTools examples here, showcases the phase transition from beta to alpha titanium. So we have this initial phase map where we have almost only alpha phase, so 99.7%, and a tiny bit of retained beta phase. And we can then use something that's called a triple point reconstruction, where we actually look for triple points between alpha. And if we look at this inverse pole figure here, where we have the misorientation axis between alpha variants, and then the fit of the disorientation with the OR, we can see that we actually have distinct misorientation axis between the different variants in alpha, which is not the same in martensite in steels because of the high symmetry of the child phase. Here alpha is hexagonal, so we can actually, if we find three variants, we have like at least two misorientation axes, and based on those misorientation axes, we can then do a reconstruction. So this is another way of reverting this microstructure by looking at triple points. Doesn't work for everything, but it works quite well for FR titanium, and then we get this reconstructed microstructure in the end. Then the fourth example is cold-rolled high manganese steel. So we have an austenitic microstructure that transformed to epsilon martensite, and then epsilon martensite further transforms to alpha prime martensite. So we go from FCC right here to a hexagonal martensite, and from hexagonal we go further to a body-centered tetragonal martensite. And actually we have two martensitic transformations here, and we can actually use this reconstruction to do a two-step reconstruction of the microstructure. So we can go from child alpha phase to epsilon in the reconstruction. This gives us this reconstructed epsilon phase, which looks quite reasonable. And then we can go from epsilon, from this reconstructed epsilon to gamma. And at the end, we can get a reconstructed microstructure that looks quite good, I would say. And so we can, it's so flexible, the algorithm, that we can go through several steps of phase transition. So the last example is intercritically annealed martensitic stainless steel. This is a material I've been working with a lot, and we have this martensitic microstructure here with almost no retained austenite, but then when we anneal this microstructure, we actually start forming some austenite on the boundaries between the martensitic laths here. And it turns out that the orientation of the austenite that forms during this annealing process is actually the same as the prior austenite orientation. This is usually called the austenite memory effect. So from this microstructure, since we already have this kind of annealed austenite, we can also then use a growth algorithm, the one with the loop down here, to reconstruct the entire microstructure. We could also use the clustering algorithm, but this is just a lot faster and easier to do. But both basically give the same result. And then in the end, we can also plot variants and packets and do all the analysis we like to do with our other microstructures. So I think I've shown you 5 nice examples, one of them in a lot of detail to show how this reconstruction in MTEX actually works. I think we've developed a versatile framework for analyzing phase transitions in MTEX 5.6. The implementation is implemented in a class with modular methods and properties. Depending on the microstructure, different reconstruction strategies can be chosen, which is quite powerful. The reconstruction is automated as much as possible, while maintaining full user control over the reconstruction process. So we automatize to a step that we can still have control over everything. Then ORTools is an add-on to MTEX with some additional capabilities for analysis of martensitic microstructures. And probably to do in the future, I've not really coordinated this with Ralph, but what I think should be done in the future is to prove the reconstruction accuracy for martensitic microstructures and steels. So I think the next speaker will talk a little bit about that. This is still a problem. We could do this by considering local grain boundary misorientations or experimenting with different clustering algorithms. We could do an implementation of transformation texture prediction. This is already possible in ORTools, but it would be cool to do this from ODF to ODF and also do available work and variant selection analysis. And maybe you have also some suggestions of what you still think is missing in the functionality. So thank you for your attention.